The notion of continuity in the previous videos. In this one, we are going to talk about a stronger notion called uniform continuity and explore some of the implications of uniform continuity. Alright, so before we begin, let's quickly recall the definition of continuity itself. We say that a function f is continuous at some point x0 within its domain if the following condition is satisfied, right? Namely, that for any epsilon greater than 0, I can come up with a delta such that for all x which is within a delta distance of x0, the distance between the function values at x0 is going to be within epsilon. Right? In other words, whatever threshold epsilon I pick on the gap between the function values, I can come up with a delta such that so long as your argument lies within a delta neighborhood of x0, the gap between the function values is also guaranteed to be less than epsilon. And this is what is capturing the intuition that as x approaches x0, f of x approaches f of x0. So as you get closer and closer to x0, the function value gets closer and closer to f of x0, right? Which is what implies continuity. Now the main thing to note here is that the choice of delta that you're able to produce clearly depends on epsilon, right? The smaller the epsilon, in general, the smaller will be the delta, right? You need to be that much closer to x0 to guarantee that the function value is, well, within some smaller epsilon distance of x0. So this delta that you produce clearly depends on, sorry, but in general it can also depend on x0. Right, so in the original definition of continuity, the delta, all of this is basically specialized to the point at which I'm actually looking to argue continuity, right? So the delta clearly depends on epsilon, but can also in general depend on the precise x0 that you are trying to prove continuity at, right? So what uniform continuity does is basically eliminate this dependence on x0. So this dependence on x0 can be thought of as a location dependence, right? So eliminates this location dependence. Okay, so with that, let me give you the formal definition of uniform continuity. Let S be some subset of the domain of the function f. We say that f is uniformly continuous on S if the following condition is true. For any epsilon greater than 0, there exists a delta greater than 0 such that if you pick any 2 points within S which are delta apart, the function values are guaranteed to be at most epsilon apart. So there exists a delta greater than 0 such that xy belonging to s x minus y being less than delta absolute value implies the gap between function values is at most epsilon. Okay, so the important thing to note is that delta doesn't depend on location here. You give me an error threshold between function values epsilon, I will produce a delta such that if you pick any 2 points which are delta distance apart within the set S, well, the function values are guaranteed to be at most epsilon apart. Okay, so that is the definition of uniform continuity. It is a straightforward takeaway for you to see that uniform continuity is in fact stronger than continuity. In other words, uniform continuity implies continuity. So f is uniformly continuous on S implies that f is continuous on S. right? So this is yeah, it's a straightforward consequence of the definition. Stare at the definition and convince yourself that uniform continuity implies continuity. All right. Another, well, quick definition is to say that we say the function is uniformly continuous if it is uniformly continuous over its entire domain. So we say f is uniformly continuous, right? So if I don't specify a particular subset of the domain when referring to uniform continuity, it means that the function is uniformly continuous over the entire domain. If f is uniformly continuous, on its domain. Okay, so very quickly once again, uniform continuity means that it's continuity, but with the additional condition that the delta cannot be location dependent, right? So which means that you give me an epsilon threshold on the gap between function values, I can give you a location independent delta in response to that, such that so long as you're within it, so long as you take any two arguments to the function which are within delta distance apart, you are guaranteed that the function values are at most epsilon apart. Okay, so having now seen and absorbed the definition, let's go through a couple of examples. So the first example we will consider is f, let's say over the interval 0 to infinity to r, such that f of x is equal to 1 by x square. Okay, so this is the first example we will take, and my claim is that f is uniformly continuous on sets of the following kind. So if you pick any a that is positive, and if you look at intervals of the form a to infinity, a included, f is uniformly continuous on, well, sets like this, on subsets of this form of the domain. Okay, so how do I go about arguing this? For a given epsilon, I need to produce a delta such that any 2 points from which are greater than equal to a, which are within delta distance of one another, will have a function will have function values which are also within epsilon distance of one another, right? So for this, let's first start off by trying to bound the gap between f of x and f of y, and to do this, of course, I pick xy greater than or equal to a. Okay, and now let's try and bound f of x minus f of y. Now f of x minus f of y is, of course, absolute value of 1 by x square minus 1 by y square, which you can easily simplify to x minus y into x plus y upon x square y square. All right, with one more round of simplification, I can write this as follows. This is x minus y upon, well, x square y plus xy square. Okay, and now I observe that since x and y are greater than or equal to a, both the terms x square y and xy square are at most are greater than or equal to a cube, and so the reciprocal, the reciprocal of that is at most 2 divided by a cube. Right, I hope this is clear. All I'm saying is that each of these pieces, x square y is greater than or equal to a cube, xy square is greater than or equal to a cube, so the entire denominator is greater than or equal to 2 times a cube, right? So I should put the 2 here. Sorry about that. Yeah, okay, so this is now upper bounded by absolute value of x minus y divided by 2a cube. Okay. Seem to have made a mistake here. Yeah, I made a mistake here. All right. So let me, maybe what I'll do is I'll just redo this bit of the calculation quickly. So f of x minus f of y is equal to, well, 1 by x square minus 1 by y square, right, which is of course equal to x square minus y square upon x square y square. So that's the bit I write as x minus y into x plus y upon x square y square. Okay, now I write this as x minus y into not, yeah, the mistake was here, right? This is not correct. So it should have been 1 by x y square plus 1 by x square y. Yeah. Now the point is that each of these terms is going to be greater than or equal to, well, the denominators xy square and x square y is greater than or equal to a cube. So their reciprocals are less than or equal to 1 by a cube, right? So therefore this indeed can be upper bounded by 2 by a cube times absolute value of x minus y. Okay. So now we are almost done, because we have already argued that the gap between the function values is in some sense bounded in terms of simply the gap between the points x and y. So now what I would do is, given any epsilon greater than 0, well, I will set delta as follows. I will set delta to be a cube by 2 epsilon, right? And well, I leave it to you to verify that indeed if you pick x minus y to be less than delta, that will imply that the gap between the function values, given the bound that we have derived, is in fact less than epsilon, right? So given any epsilon, I have produced a delta. That delta in fact is just a cube by 2 into epsilon, such that the condition for uniform continuity applies, right? So that completes the argument that indeed this function f 1 by x square is in fact uniformly continuous over sets of this form, okay, a to infinity. So in particular, if I take a to be 1, it means that from the interval 1 to infinity, 1 included, f is uniformly continuous. Okay, now we can actually also construct an example where a uniform continuity does not hold, essentially using the same example. Okay, so let's look at the second claim. The same function f is not uniformly continuous on, for example, an interval of the form, on the open interval of the form 0 to 1. Okay, so for example, from 1 to infinity, this fellow is uniformly continuous, but from 0 to 1, it is, however, not. Okay, so now let us see how it is that one would go about showing this. Maybe I'll move to the next page for the proof. So the claim, recall, is that f of x equals 1 by x square is not uniformly continuous on the interval 0, 1. Okay, and the way one would go about doing that is the following. So consider basically the gap f of x minus f of y for, well, points of this form. X is equal to 1 by n, y is equal to 1 by n plus delta. Okay, so these two guys are delta, exactly delta apart. X is 1 by n and y is 1 by n plus delta, right? Now if you look at the gap between the function values, which is f of 1 by n minus f of 1 by n plus delta, well, the same calculations that we did before basically would give you that this is equal to delta into delta plus 2 by n upon 1 by n into 1 by n plus delta. Alright, yeah, I leave this for you to just make a trivial calculation for. The point here is that for whatever fixed delta you choose, this fellow, because of the 1 by n sitting out here, will actually go off to infinity as n goes to infinity. Okay, so the moral of the story is that if you choose x and y in this manner, mind you, they're always delta apart. Whatever that delta might be, however small it might be, you are guaranteed that the gap between the function values goes to infinity as n goes to infinity. In other words, as x moves closer and closer to the origin, the gap between f of x and f of y blows off to infinity, right? Which implies that in fact, it's impossible to find a delta that would work for whatever epsilon that you pick. So no delta would satisfy the condition for uniform continuity, no matter what epsilon you pick. So for example, for epsilon equals 1. Right? So if it were uniformly continuous, then for, let's say, epsilon equals 1, you should be able to give me a delta such that any 2 points in the interval 0 to 1, which are delta distance apart, would satisfy the condition that the difference between the function values is at most 1. Right? But here we know that if I just take the points 1 by n and 1 by n plus delta, as n becomes large, in other words, the former point goes closer and closer to the origin, the gap between the function values goes off to infinity. So it couldn't possibly remain bounded by 1. Okay, so that completes the argument that the function 1 by x square is in fact not continuous, not uniformly continuous in the open interval 0, 1. Right? Remember, this fellow is continuous. 1 by x square can easily be shown to be continuous in the interval 0, 1. However, it is not uniformly continuous. Right? However, if you take intervals of the form, let's say a to infinity, where a is positive, the same function is in fact uniformly continuous. Okay, so that is those are two examples, one where there is uniform continuity and the other where there isn't. Okay, so next we are going to basically prove a one condition under which uniform continuity is guaranteed. Okay, if f is continuous on a closed interval AB, then f is also uniformly continuous on AB. Okay, so if you have continuity on a closed interval of the form, let's say a comma b, then you also have uniform continuity, right? So in general, uniform continuity implies continuity, but if you have continuity on a closed interval, then you also in fact have uniform continuity. Note that this is not a contradiction to the example that we have just above on the same page, because in that case we have a function which is continuous on an open interval 0, 1. Right? So there we had a function which is continuous on an open interval but not uniformly continuous. However, if you are working with closed intervals, what the theorem that we have just written claims is that continuity implies uniform continuity. Okay, now let's go through the argument for this. So this proof is going to work via contradiction. So suppose, with the intention of getting a contradiction, that f is not uniformly continuous on the interval a to b. Okay, now what does the negation of uniform continuity imply? That there exists some epsilon greater than 0 such that it is not possible to produce any delta that satisfies the condition, right? In other words, there exists some positive epsilon such that for any delta greater than 0, there exist x and y in the interval under consideration such that, well, x and y are within delta distance apart. However, the function values are in fact greater than or equal to epsilon apart. Right? So again, it's important to understand that this is in fact the correct negation of the property of uniform continuity. So if it's not uniformly continuous, then there should be at least one epsilon such that I cannot possibly find a delta that satisfies the condition. In other words, for whatever delta I might choose, delta greater than 0, there exist 2 points x and y which are within delta distance apart, but with the function values being greater than or equal to epsilon apart. Right? So this is in fact the negation of uniform continuity. Right? So now what I can do is, well, for various values of delta, I can therefore choose these points x and y. So for all, let's say, natural numbers n, there exists, let's say, xn, yn such that, well, xn and yn belong to the interval under consideration, and xn minus yn is less than 1 by n. However, the gap between the function values is greater than or equal to epsilon. Right? So we are building on the hypothesis that f is not uniformly continuous. Right? So there is some positive epsilon such that no matter what delta, for any positive delta, I can find 2 points x and y which are within delta distance apart such that the function value is greater than or equal to epsilon apart. Right? Now what I'm doing is choosing delta to be 1 by n for different natural numbers n. Right? So if I choose delta to be 1 by n, the 2 points I'm denoting them by xn and yn. So in this case, xn and yn are at most 1 by n apart, but their function values are in fact at least epsilon apart. Okay, so now we are going to use the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem, there, see, remember xn and yn are now bounded sequences because they are both sequences in the interval AB. So therefore, by the Bolzano-Weierstrass theorem, xn has a convergent subsequence. Let's call it xnk. Okay, so there is some subsequence of the xn sequence which converges, right? So therefore, we know that if you look at x and k, as k goes to infinity, this will converge to some limit p. And again, as we have argued before, this because xn lies completely in the closed interval ab, you are also guaranteed that this p will lie within the closed interval ab. Okay. Now, since x and k and y and k are close, in other words, x and k minus y and k in absolute value is at most 1 by nk, it also follows that as k goes to infinity, the subsequence y and k also converges to p. Okay, I leave this for you to check. It comes from the fact that xn minus yn is at most 1 by n. Right? So if xn has a convergent subsequence, then essentially the same subsequence for the yn sequence is also convergent and moreover, well, converges to the same limit p. Okay, so now given that I have continuity, this implies that f of x and k converges to f of p, and f of y and k converges to f of p. Okay, but this contradicts the fact that f and k, f of x and k and f of y and k have to always be greater than or equal to epsilon. Right, so this So this contradicts this condition. And that completes the argument. Okay, so what we have, so I hope this is clear. What we are showing is that suppose that f is not uniformly continuous, then in fact I can construct the sequences xn yn such that xn minus yn is at most n, and f of xn minus f of yn is greater than or equal to some positive epsilon. Right? Now I use the Bolzano-Weierstrass theorem to argue that there must be a convergent subsequence of the xn sequence, but then the way xn and yn are constructed, you are guaranteed that the same subsequence of yn also converges to the same limit p. So therefore by continuity, f of xn has to converge to f of p, f of xn k has to converge to f of p, f of yn k also has to converge to f of p, which means f of xn k and f of yn k have to get arbitrarily close to one another, which they can't because, well, they are guaranteed to be greater than or equal to epsilon apart, and that therein lies your contradiction, right? So the moral of the story here is that continuous functions on closed intervals are in fact continuous. Okay, so that was the main result I wanted to prove in this video. What I want to do is conclude with one final example that kind of motivates why uniform continuity is important, right? So this is just an example. We will come back to this a great deal in the future, but we will talk about integration in the future, but this is just a motivating example for why uniform continuity is actually a useful concept. So suppose that f is continuous on the interval, let's say 0, 1. Okay, now I want to define the integral of the function f over the interval 0, 1, right? As we will see, the way in which you do this is by making so-called Riemann approximations of the function. So this is f, let's say, this is 0 and this is 1, right? So the way in which you construct a Riemann approximation is as follows, right? You break up the interval 0, 1 into a bunch of chunks. You know, for ease of illustration, I'm going to break it into just 4 chunks. So these points are 1 by 4, 1 by 2, 3 by 4, and so on. Right? In general, I would break it into n chunks, and then what I do is then within each of these sub-intervals, I'm going to basically approximate the area under the curve by basically a rectangle, right? An upper bounded rectangle and a lower bounded rectangle. So in particular, I take the largest value in one of these sub-intervals, right? And then I take the area under the larger rectangles, and I think of that as an upper approximation for the area under the curve. Similarly, I also do take the minimum value in each of these rectangles, and I take the area under that, and the hope is that as these intervals become finer and finer, the gap between the lower approximation and the upper approximation becomes closer and closer. Right, and that is how you go about defining the integral. Now we will do this all a great deal in detail in the future. At this point, all I want to do is illustrate how uniform continuity plays a role. Okay, so here is how I would define the upper approximation to the area under f. So let's define un as 1 by n times summation from 0 to n minus 1 m of I comma n. Okay, I'll define these things min in a bit. Similarly, ln is equal to 1 by n summation 0 to n minus 1 min, where min is in fact the supremum of the values taken by the function in the interval from I by n to I plus 1 by n. Similarly, min is the infimum of the function values taken over the same interval. Okay, so what have we done at this point? So I claim that, so I break the interval 0 to 1 into n chunks. Right? Each of these chunks is basically of length 1 by n. So the ith chunk, ith subinterval runs from I by n to I plus 1 by n. Okay. So now, what is this UIN? What is this UN? Sorry, it's basically, if you look at the summation here, the summation is basically the sum of the supremum values within each of the subintervals, right? That into the length of the subinterval, which is 1 by n. It basically gives you an upper approximation for the integral of the function. To let me just say area under the curve. Okay, I hope that kind of intuitive understanding of integration everybody has, that we think of the integral of f as basically the area under f, right, from 0 to 1. So clearly un is going to be some upper approximation to the area, and similarly this is going to be a lower approximation. Why is this a lower approximation? Well, for every interval of length 1 by n, I am basically multiplying the length of the interval with the infimum of the function values taken over that interval, right? Which is what these small mins are, right? So I should expect that ln and un, if the integral has to be well defined, I need this upper approximation and the lower approximation to become closer and closer. So to define, let's say, the integral from 0 to 1, we need that un minus ln goes to 0 as n goes to infinity. In other words, as n becomes larger, the subintervals become smaller and smaller. The gap between un and ln must in fact become smaller and smaller, right? And the point I'm trying to make in this entire example is simply the following. Uniform continuity of f implies exactly this. Okay, so you need uniform continuity to argue that the gap between un and ln actually goes to 0 as the intervals become progressively finer, right? So this is my claim. Okay, so this entire example is basically set up in such a way that I've defined un, defined ln. The motivation for defining un and ln is in order to go about defining the integral of the function. Okay, that motivation will become clearer later, but the precise claim I'm making is the following, that the uniform continuity of f over the interval 0, 1 in fact implies that un minus ln actually goes to 0 as n goes to infinity. Okay, so this is my claim, right? And hopefully it provides some motivation for why uniform continuity is important, because if you to define the integral, I need this un and ln to become basically close to one another. Okay, so how do I prove this claim? Given any epsilon greater than 0, by uniform continuity there exists a delta such that x and y, which are within 0, 1 and within a delta distance of one another, implies that f of x minus f of y is less than epsilon. Okay, this follows from the definition of uniform continuity. Now what I do is pick n such that 1 by n is in fact less than delta. Okay, so my claim is the following. For n greater than or equal to n, if I look at the gap min minus min, remember this is the guy that goes into the upper approximation un, this is the guy that goes into the lower approximation, right? Now what is this? This is the difference between the maximum value taken by the function and the minimum value taken by the function. So in fact it's the gap between f of alpha in, right? This is the maximizer over the interval I by n to I plus 1 by n minus f of beta in. So this is the maximizer over let's say I by n and I plus 1 by n. Similarly, this is the minimizer over the same interval, right? So the gap is in fact the gap between the maximizer and the minimizer. But remember, the maximizer and the minimizer are at most delta apart, right? Because I have chosen my interval to be small enough such that the gap of the interval, the subinterval, is at most delta. So therefore the gap between these two is also at most epsilon. Okay, and once I have this, well, it turns out that un minus ln is simply, after all, 1 by n times min minus min. Yeah, so un minus ln is, after all, simply the average of the differences between capital min, the supremum over the subinterval number I, minus the infimum over the subinterval I, right? Each of these guys is less than epsilon, so the average of these is also less than epsilon, right? And that essentially completes the argument. Why? Because for any epsilon greater than 0, I have picked a capital N such that for all n greater than capital N, un minus ln is in fact less than epsilon, which in fact implies that the difference between un and ln goes to 0 as n goes to infinity. Okay, so at this point, all I need you to understand is, given that un and ln are defined the way they are, uniform continuity implies that the gap between un and ln goes to 0 as n goes to infinity, right? We will have a lot more to say about upper and lower approximations to the area under f, and therefore the precise definition of the integral going further in the course. Okay, so we'll stop here. There are a couple more implications of uniform continuity that we'll explore in the next video.